gigabit per second. Everyone loves throwing that number around. That's like, you're not a real IDS unless you can do 1 gigabit. Well, 1 gigabit's a whole lot of bits. I mean, it's a lot of bits. It's a gigabit. And out of that many, sorry, a gigabit is a whole lot of bytes, a whole lot of megabytes, a whole lot of packets. And when it comes down to it, if you're trying to actually, if you have an IPS product and it's supposed to pass packets, you have to pass 1.6 packets per microsecond to keep up with the gigabit per second of traffic.
Oh, and by the way, anybody deploying gigabit is not going to deploy gigabit in one way. They're going to do full duplex gigabit.
Which,
and
of
so
course,
double it.
Now you have both cards have to take a packet in, process it, get it back out again, and now you're down to 3.2 packets per microsecond because it has to come in this side, process there, then go the other way. So unless your engine can actually process 3.2 packets every microsecond, it's not going to do 1 gigabit. And there's a lot of people build their IDS and IPS products up for standard PC hardware. There's limitations on things like the PCI bus and the PCI-X bus where you just really can't transfer that much data. If someone's using an old PCI bus that runs at 33 megahertz and they're not using like a really fast server card, it doesn't really matter what number they tell you, they're still limited to the bus speed of the PCI bus itself. Even if you're using a 100 megahertz 64 byte bus, you can only get 800 megabytes per second through that bus. And that's megabytes, not megabits in this case. So there's definitely real limits. Most people are actually only using either 32 or 66 megahertz at either, they can usually get up to 266 or in some cases up to 532 megabytes per second. But for the most part, it's about 266 and 133 is about standard. You also run into interrupt limits. Every time a packet comes into the system and it's not running in polling mode, it triggers an interrupt in the software. The software then has to go process the interrupt and process the packet and so on. You actually hit certain hard-coded limits in whatever the operating system is, whatever the hardware is, that you can't process more than 680,000 packets per second coming in on the receive interface, and you can't send more than 840,000 packets per second out unless you're using a polling mode card or using a custom driver or hardware that's really designed for this type of thing. And a lot of people selling these IDS and IPS appliances don't have hardware that can do that. If you're trying to capture 64-byte packets, each one of those triggers an interrupt, and the maximum megabits per second you can capture at 64-byte packets is 348 megabits. That's just the numbers. If you say you can do more than that, you're lying at 64-byte packets. So a little bit about realities on hardware appliances. A certain vendor uses a dual Intel Pro with 100 cards in their appliance. That's a pretty beefy Intel card. That's about as good as it gets when it comes to PC quantity hardware and network cards. They've got a 3 gigahertz Xeon processor on that box. It's your standard Dell 1U rebranded appliance. The max capture mode for that box is 760 megabits per second. That's just as fast as that hardware can go. Whatever that vendor tells you otherwise, it doesn't matter because that's what the hardware can do. Unless they've got some magic wormhole going from the CPU to the network card, it's not going to happen. If you're in inline mode, you only get half of that because the packet doesn't come in one side, go back to the other side. So you only get 380 megabits per second max. And as we saw with the recent ICSA report, the ICSA did basically a rating test in different appliances to figure out how fast they really could push traffic and still do accurate intrusion detection and intrusion prevention. With the ISS G400 Preventia, it was only rated at 340 megabits, even though they sell it, I think, as a 4 gigabit appliance. So it really depends on. It doesn't really matter what the vendor tells you. If they're running hardware like this and running on off a standard PC platform, there's only so fast they can go, regardless of what the marketing speak says. With any hardware, especially with dedicated appliances where you have like custom processors, FPGAs, that type of thing to speed things up, you've got what's called the fast path and the slow path. The fast path is what basically never reaches the management processor of the system. If you've got a router like a Cisco router, most of it goes through the fast path. The fast path comes in one interface, matches a little rule. If it doesn't match that rule, it goes straight back out the other interface. It wants to push packets as fast as it can. If you can trigger some kind of exception or anything that requires any kind of processing by the management CPU, it goes into what's called the slow path. The slow path, it goes straight through the management CPU, and the CPUs on these boxes really aren't that fast. Mostly for heat reasons. If you have a really small appliance or a Cisco router, that thing's either running like a small MIPS chips or PowerPC chip or some kind of x86 chip that's just really not clocked that fast because of thermal considerations. So if you can find a way to consistently trigger exceptions or consistently trigger the slow path on a box, it doesn't matter how fast it can process on the fast path, that little CPU just can't chunk that much data. A good example is management services. If you take an IPS appliance and you start flooding the web UI, just the built-in Riata web service or mRouter, depending what operating system you're using, whatever built-in web service it has, just pound it with Apache Bench, and then try to pass traffic through the fast interface. A lot of times you'll see a massive slowdown on how many packets per second it can process just by hitting the management interface at the same time. You don't really have to do anything but do GET requests, and that's using enough CPU that if there's any kind of exceptional condition like fragment processing, it runs out of CPU and you resource starve the box. Another interesting thing about hardware development, if you're building custom appliances, is something called a core. If you license a certain chip, oftentimes the vendor will also license certain cores for it. The cores are different software modules you can license for that chip to do a specific task. So you're trying to build an appliance that does firewalling and NAT and routing and all these other fun things. Whoever you go to as your vendor for it will say, okay, well you're using Altera or using Broadcom or using Intel. We'll sell you our cores for $5,000 for the license for all this or whatever it happens to be. They'll sell you a switch chip or a switch core, and that does switching. Another one does something else. Well, because so many vendors using these cores, they become a really good target for doing things like resource attacks, denial of service, and otherwise trying to find vulnerabilities in these cores themselves. So if someone gets access to these cores, say you work at a company that's doing custom hardware development, and you get access to these cores and start auditing them, you can find really interesting bugs that apply across multiple vendors in terms of resource starvation and vulnerabilities and fragmentation issues with these cores. Memory allocation is another issue. If you're working on any kind of appliance through IDS, you don't want it, standard malloc doesn't apply. You're not going to say, oh, another packet, let me malloc some bytes, because the overhead of doing that isn't worth the performance hit, really. What you end up doing is creating static buffers, or what we call buckets, that are the maximum size of whatever packet you're going to put into that buffer. So if the packet's between a certain range, like say 1 and 128 bytes, you'll put it into the 128 byte bucket. And then it's in a certain one, you'll do the next set, the next set, and the next set. So what you can do is actually flood a system with various size packets close to those, modulo 2, power of 2 boundaries, and you can find ways to allocate all the buckets in a given group and make it run out of memory just by sending a really small amount of data. So, for instance, the maximum size of an IP packet is 65K. So if you send anything over about 2,000 bytes long, it's going to have to use the biggest buffer possible to allocate the rest of that packet because it thinks it's fragmented to put it back together again. So you can use up all those buffers real quick. And then you go to the next one down, the next one down, the next one down, and then you flood the system, then you do your attack, and it can't process it fast enough and it has to pass it through.
So one of the other things that you can do is you can attack the IDS tracking of streams and fragmentations directly. So one of the things you can do is a large number of IDSs do use hash tables for lookup tables of where packets are coming in. Crosby and Walsh released a paper not very long ago talking about attacking hashing algorithms with hash collisions. So a very popular IDS implemented how they were hashing TCP sessions with a very simple hash. The way they calculated the key was they XORed source IP and desk port to get their key. Well, unfortunately, there's a large number of IPs, 2 to the 16th, number of source IP, destination IP pairings that hash to the same value. So you can set a large number of distinct IP port pairings that hash to the same thing. And once you actually get inside inside that hash key, everything inside of that was a linked list. So you could force a walking of a linked list. So in their paper, they released for a certain broken IDS for a single PCAP of a number of 65K packets, they were able to make the IDS take over 43 minutes to process each packet. 43, like I said, 43 minutes is way less than 3.2 milliseconds.
Yeah.
So one of the other things you can do, a number of IDSs, both hardware and software, implement what's called a splay tree. So they used a self-balancing binary tree to store all the different states that they're handling. So they didn't want to have the problems of hash collisions. So they used a splay tree, which amortized the cost of balancing the tree across the time. So what happens in a splay tree is the most frequently used nodes are bubbled up to the top of the tree. So the person on your network who's talking the most is going to be at the closest to the top of the tree. So it takes the least amount of time to search for them. Unfortunately, because it's amortized across time, you could force it. Well, the worst case scenario is ON, so to rebalance. So we have a nice demo of attacking a splay tree. All right, so I went ahead and used the UBI splay tree, which is what a number of the IDS vendors are using. So it's a very simple splay algorithm. So, and I wrote a very simple splay tree implementation. All it does is it takes all the inputs that you're sending and insert into,
Yeah, sure.
Yeah. Is that any better?
Bigger, lower, bigger? Okay. So you look like a Commodore 64 here in a second. Is that better?
All right. Like I said, it's a very simple. It just inserts into the tree everything on the command line. So like I said, and I print out every time that you splayed that the tree does a rotate. So it takes when there's a rotate action, it prints it. So one of the great things so I have a. So if you just make it do 1 through 1,000, so insert 1 through 1,000 to the tree. It does a number of inserts, and you see it print whenever it does an insert. So I do a grep-c rotate. This will tell me every time that it rotates, so it does a move inside of the tree. So it does 999 rotates. So okay, yeah, every time I do an insert, I'm saying take this and put it at the top. Makes sense. Well, the great part is, so the worst case scenario for a splay tree is if you do the same thing multiple times. So if I do 1, 2, 3, 1, 2, 3, I see that I rotate multiple times when I insert the first one, or when I insert the second one. So what happens when we do 1 through 1,000 and 1 through 1,000 again, which is so we see a large number of rotates in here. I'll go ahead and pipe that to the grep stress again, or rotate. We know we inserted 1 through 1,000 2 times, and now we have 5,000 splays. So what we've essentially done is we made the IDS reorder the tree over 5,000 times for 2,000 inserts into the tree. And actually, it's 1,000 inserts and then 1,000 lookups. Well, if you can control the network and you can control the data that's going past the IDS and enforce it in a certain order, and then enforce that order again, you can cause a worst case scenario rebalance of the tree on demand. So, and if that's happening live and the IDS is having to queue packets in their buffer, well, the splaying takes a large amount of time. The larger amount of time that you can make it splay, the more time it's going to spend splaying, more time it's going to take, and it's going to eventually drop more packets. And if they're in an inline mode, a number of hardware vendors that are implementing splay trees, if you take too much time to process a packet, it says, okay, go ahead and pass that through, because it must be valid because I'm stuck and I don't want to drop the session. So a number of vendors handle that. Otherwise, you just drop the packet and you can make the IDS just drop the session. And a number of IDSs that are implemented in IDS mode have what's called session pickup. So if a session, they know this session died, so they just drop it. Well, if they see a session start up in midstream, so say they turn on the IPS mode. Well, if a session was already in line, it was already starting, you were already doing your communication, well, they will continue. They will say, hey, this session's already valid, they're already doing something, I'm just going to let it continue. Well, if you can force the IDS to drop the packets, so it says, hey, this session's now dead, and then the next time the next packet comes in on your session, it's going to say, hey, this is a new session. I'm going to go ahead and let this through. If that was midway through your attack, you've now just bypassed your IPS. So one of the other things you can do, you can attack the pattern matchers directly. So most IDSs are implemented with some sort of string matching. So there's a number of ways you can attack the pattern matching. The first one is you can find the most expensive operation, make it repeat it over and over and over again. So if there's a broken rule that does something really bad, force that to happen again and again and again. The more CPU time it takes, the less time it's processing all the other packets. So if your valid attack is sitting in the queue waiting to be processed, again, like I said, a number of IDSs, if it figures out it's going to start dropping packets, it'll just pass what it has in its buffer because it needs to catch up.